Everyone, so this video is all about Shapiro reaction, and here we'll discuss the mechanism, its important features, and also the difference with the another reaction with which it has some similarity, and that reaction is Bamford-Stevens reaction. So it's my suggestion, if you watch that video first, it will be easy for you to understand this one, because we are also going to discuss the difference between Shapiro and Bamford-Stevens reaction. For Bamford-Stevens reaction, you can click on the link right now, and also I will give it in the description box. There you can find it. Let's start Shapiro reaction. So for Shapiro reaction, here we have taken the substrate aryl sulfonyl hydrazone. So this molecule you can prepare starting from the corresponding carbonyl compound, and we have to take this hydrogen H2N NH and then SO2R. Now here I have written the general structure AR because this AR it may vary. So what type of AR we can have? We can have tosyl group. So this group we have seen in the previous reaction, which is Bamford-Stevens reaction. But sometimes in this case, this trisyl group, where try to understand the difference, here we have methyl group at 4th position, but we have in this case 3 isopropyl group. So this type of isopropyl group, it is helpful. Why? Because here we are using this type of bases RLI, that is, it may be secondary butyl lithium, tertiary butyl lithium. So in this case, ortholithiation chance is there if ortho positions are there is hydrogen. So that is the reason sometimes this type of group, if it is present, it is helpful. So trisyl group is taken when we are using this type of base. That is in Shapiro reaction, because in Bamford-Stevens reaction we do not use this type of strong bases. So two equivalent of strong base. What type of base? RLI, secondary butyl lithium, tertiary LDL, lithium diisopropylamide, and then we have Grignard reagent. So these are the different possibilities for base. So first there will be formation of vinyl lithium, and the same position where the CN double bond is present, at the same position we will have this carbon Li bond, and in the that is adjacent position we will also have this CC double bond. So together we are calling it vinyl lithium. Now this is not the end of the reaction. You can also have some electrophile, and that is the beauty of this reaction. You can have so many different types of you can introduce electrophile. Sorry, there will be E. Now different types of electrophiles, what are the possibilities? We will also see it in separate slide. So here vinyl lithium will be produced first, and then E plus will be introduced. Okay. So in a nutshell, what we can say, as if starting from this we are getting finally this molecule, and if you do not want to use an electrophile, then in this position there will be H, and that H can come from solvent. So this is the overall reaction, starting as if we are making this carbonyl compound directly to CC double bond, where the position of CC double bond will be adjacent position. Now which side it will be formed, that will differ, that is based on the substrate. And here you can also introduce this electrophile. Now unlike Bamford-Stevens reaction, when we consider regioselectivity, here less substituted product will be formed. Though from this general structure you will not be able to understand, but when actually we will see the mechanism, it will be clear to you. So this is a major product, kinetic product of less substituted CC double bond. Stereoselectivity is mixture of EZ, but sometimes in some places you can see in some books also it is mentioned that Z is preferred. Now why Z is preferred? It will be clear in the mechanism part, but mostly it is better to say that it is always mixture of E and Z. The reaction is somewhat similar to this, as we have already said it. So let's okay, so one thing I have missed here. Better you use this trisyl group because it avoids the ortholithiation. So the reason I have already said, and it is also mentioned here. Okay. Mechanism of Shapiro reaction. So here we have taken the base butyl lithium. In presence of this base, and look at this substrate, I have taken not any general structure. This is I have taken intentionally because here both side we do not have same type of groups. Different groups are there, right? So that is why. So that we are able to understand which side the carbanion, that is a negative charge, will be produced. So first, in presence of butyl lithium, because we have taken two equivalent, the first equivalent will remove this H. So that is why there will be negative charge generation over this nitrogen. Now see, this molecule is already carrying some negative charge, and if you want to produce another negative charge, obviously you have to use some strong base, and that is the reason in Shapiro reaction When we are generating the second negative charge, we have to use strong base, unlike Bambo-Steffen reaction. Now the second butyl lithium, it will capture this hydrogen. So it will prefer that position where it is less sterically hindered, and also that hydrogen which is basically more acidic in nature. Okay, so that hydrogen will be lost. So here we have negative charge at this position. So the second deprotonation, that is this hydrogen, when it will be removed, that takes place syn to SO2N. So this group, syn to this, it will be removed. Why? Because see, when negative charge over N, that means Li plus is already present in the medium. So there will be this type of chelation. Now if the second negative charge is also produced this side, chelation will be favored. So that is the reason the second deprotonation is also taking place to this side. And this can be also another reason why we always get that is Z product sometimes can be major, because see, these two large groups, they are already towards the same side. So sometimes Z group may be present, but ultimately that also we cannot say that is clearly, because if this group is, there is some steric hindrance, final product may be trans also. So we cannot say exactly that Z will always be major, it may not be so. Then we have this negative charge over N. Now this carbon negative charge over carbon, if it is making a CC double bond, this CN double bond will be broken, NN double bond is produced, and this group will be removed. So SO2AR group is removed, and we are getting this type of structure. And finally this negative charge, it will make NN triple bond, and CN bond is broken, negative charge is over this carbon. So this carbon now, negative charge means there will be it will be associated with lithium. You can also write it like this, as if negative charge is here. And finally, in presence of E plus electrophile, we will get this type of final molecule. But if you are not using any E plus, then it will be simply hydrogen in place of E. So this is the less substituted vinyl lithium that is produced, and here we can understand why the less substituted one is the major product in case of Shapiro reaction. So less substituted alkene is formed since the least hindered alpha position. So this is alpha position, this is alpha position. The least hindered alpha position is the most likely position for deprotonation because it is under kinetic condition, and internal chelation of the organolithium with the nitrogen that can also stabilize. So these two are the reasons for which less substituted alkene will be preferred. Now what are the probable electrophiles and the corresponding products? So here we have, this is the vinyl lithium, remember. From this vinyl lithium, depending on what type of electrophile you are using, here we have taken DMF. Then if you are taking some acidic proton containing compound, that is acetic acid, H2O, D2O, we have H or D. Then if you take Me3SiCl, then the electrophile that will be inserted is SiMe3. So this part is the electrophile, this part is the electrophile. As a whole, it is the source of electrophile, but E plus is HCO or Me3Si. And if you are taking this type of ketone or aldehyde, we can also get alcohol. So alpha beta unsaturated aldehyde we are getting when you are taking DMF. Then vinyl silane we can get. Then we can get allylic alcohol when you are taking ketone or aldehyde. Now these are only some of the examples of E plus. There may be so many other varieties, as you can see in this table. Electrophile source, when you are taking 1 degree alkyl bromide, there will be some substitution. That is, just think in this place there will be some alkyl group. Aldehyde and ketone, allylic alcohol, from this is the example. Then dimethyl formamide, alpha beta unsaturated aldehyde, this one. If you take CO2, you will get some unsaturated acid. Chloromethyl silane we have already seen, and if it is iodine, there will be vinyl iodide. So these are the possible, there is probable electrophiles and the corresponding products. Now with the difference, we will compare these two reactions, Shapiro and Bamford. This is kinetic product, less substituted. This is thermodynamic, more substituted. Strong bases are used like this. Here the bases, they are also strong, but not so like butyl lithium LDA. 2 equivalent base and 1 equivalent base, because here we generate 2 negative charge, one over nitrogen, another one is over carbon. Now one advantage you can say we have when we compare these two, advantage of Shapiro over Bamford-Steven is that the resulting dianion which we get in case of Shapiro, there is no chance of rearrangement. But when it is Bamford-Steven, then there is two types of intermediate generation possible, carbene and carbocation, and there may be a further rearrangement. That is, for carbocation you can have some rearrangement. When it is carbene, some CH insertion is possible, but for Shapiro those things are not present. So this is one of the advantage. Now we will see some examples of Shapiro reaction. Here if you look at this molecule, you just have to focus on that part where our actual, that is where the reaction will take place. And now we are discussing Shapiro, so obviously it will be easier for us to recognize. But when in exam, there will be so many different types of name reaction you have to face. So from the reagent and the substrate design, you have to recognize that yes, this is Shapiro reaction. So this type of group must be present, CC double bond, then NHTS or tricyl group. We will have some strong base like butyl lithium or LDA. Solvents mostly taken because it is butyl lithium, ether type of solvent, THA for ET2O. So here we are getting CC double bond at this position, and this is less substituted, not to the other side. Another example we can see here. This is the part where the reaction will take place, and double bond is generated at this position because other side it is not possible. Already there is 3 substituent. The third example, here we have first we are that is some step jump is there. You have to understand the C double bond of first we will convert it to, in presence of this PHSO to NHNH2, there will be formation of the C double bond N, and then we are using this base. That is, first we are generating the Shapiro reaction substrate, then we are using strong base, and finally this is the electrophile. So the position where originally you have the C double bond O, in the same position there will be C double bond N, right? Then in the same position you will have CLI, and in the same position you will have CE. So in this way you can remember, it will be helpful for you. So these are the 3 examples. Now these are simpler. Next we are going to see some example. This is something different. It is, if you simply follow the mechanism, that is not enough. It is not so black and white, right? So see, you have to understand the substrate design. It is fine CN double bond, then NH tricyl, that is always present. Now the first 2.1 equivalent tertiary butyl lithium. So first there will be negative charge generation over this nitrogen by removal of this nitrogen, and the second negative charge that will be here. So the product that we will get, negative charge over here, then N negative, and then we have this tricyl group, and this part it will be present as it is. Now what will happen, as there is already presence of some CC double bond, that is in this molecule, so some different types of mechanism we can observe. So first I will write this. So up to this there is no difference, but you will see the difference after this. Now this CC double bond, what it can do, so there will be that is NN triple bond formation. Now this CN bond will be broken, there will be negative charge at this carbon, but I am directly writing it, negative charge will be at this position. So when there is negative charge at this position, you will get, that is at this position there will be 5-member ring generation, and at this position there will be this CLI bond. So in this way you can get this molecule. Now further, if we are treating it with E plus, this E plus may be a DMF, and then we are getting this type of C electrophile. So I have already given the page number. You can find the problem there if you want to go check the details. Then we have another example. This is also from the same page number. Here we have this tricyl group. As you can see, this is the large group we have present. Now we have taken 2 equivalent, that is fine, but see here 2 equivalent we are taking, something is different here. First there is negative charge generation, then the next negative charge it will be generated here. Now this negative charge, as we have in the medium this type of molecule, it can attack here, iodine is removed, and we are getting some CC bond. So this is the newly generated CC bond. Now we are using the third equivalent of BuLi, and this negative, now there will be negative charge generation at this alpha position, and as usual we are using some electrophile. So I plus will be generated from iodine, So finally in this position you are getting first CLI and then there will be CE. That means CI. Our E is I, right? So this is the this is how we are getting the product, but this is not so straightforward, right? So it depends on the substrate design. Now very interesting, catalytic Shapiro reaction. So why I am saying it is interesting, because see, here we have taken 0.1 equivalent LDA. In other cases what we take 2 equivalent. Sometimes it's slightly more than 2 equivalent to avoid side reaction, but here it is 0.1 equivalent LDA. So alternative to tosyl or trisyl hydrazone, here we are using this special type of group where instead of NH you have some triple bond. N is 3-member ring, not triple bond. So here N is part of this cyclopropane, right? Instead of carbon we have one carbon replaced by N. Now in presence of Et2O we are getting this type of product. But how we are getting it? You can get it in this page. So if we look at the mechanism, what is happening here? This position where the hydrogen is present, I have marked it blue specifically. In presence of LDA, this H will be captured, and in this position there will be negative charge, and that is why we have written here CLI, right? Now this CLI bond, if it is broken, there will be CC double bond. This CN double bond is broken and negative charge over this carbon. So this carbon negative charge, there will be CLI bond. You can also write it negative charge, but it is always CLI bond. CLI bond means it is CLI, C negative, as if it is behaving as carbon. Okay. So finally this CLI bond will be again broken, NN triple bond and negative charge at this carbon. So here it is written as CLI. And finally this CLI, because in the medium, remember in the first step when this N negativity is capturing this H is already there. Now this H can come again at this position where Li is present, and you are getting the final product. And when this H is already taking this Li, it is again converted to LDA, and this LDA can start another cycle. So that is why catalytic amount is enough. So this also you can get in Carruthers page. I have mentioned it. So this is very interesting, right? Because unlike 2 equivalent, we are using catalytic amount. So that's all about this video, Shapiro reaction. I hope it will be useful to you, and thanks for stopping by.